And he also seems to be a top-notch Linux user. Using one of the founders' versions of Linux. The title of his talk is very consistent with his work, mainly towards self-consistent modeling of the ISM.
Thank you. Mindful. Okay, I have a problem with my screen because I didn't have time to do something. Okay, but anyway, here you see, I'll go to my talk in a minute. It will be a short talk. And what you see is a cat on the mid-plane of the galaxy. I will explain later all the details on this. So on left, this is 1 kiloparsec by 1 kiloparsec resolution. Here is the highest resolution existing on the tiny beam, which is 0.625 parsec resolution. We start from cells of 10 parsec and we go down up to 0.625. This simulation took 9 months to be produced. Okay. So you're going to see a small timescale evolution, and basically blue is the cold gas, red is dark gas. So what you see is bubbles.
Roughly what temperatures?
10 to 7, 10 to 6 K. For the cold gas, blue is roughly 100 K. So put this on this diagram here on this side. Is there a pointer? Yes. On this diagram here, you have oxygen 6, and you'll see both movies simultaneously running.
Sorry, Miguel, how do you know this oxygen 6? From temperature range or what?
Yes, temperature, the normal issue, normal way to calculate it. I'll go on this later. This is just for you to pick up your eye on the resolution. I would suggest you just look for the cold gas and put your eye there, and also what happens inside of the bubbles. This is really important what you're going to see. Okay. This is frames of 0.5 million years. And this is running from 138 million years to up to 170 something million years. And you can see the bubbles form, supernova explode, the bubbles expand, and then they immediately disappear. So you're able to track all the instabilities going inside of the bubbles and the diffusion of the shells inwards. Right, and I also can see on this plot here what's happening for the oxygen 6.
But they disappear not because they collapse, they disappear because they move vertically, right away from
No. They move upwards, but also simultaneously they diffuse inwards. So you see this on the plane, so they're diffusing inwards. And this is an issue. You're able to track this because you're able to resolve all the cold gas and all the diffusion process. So it's faster. This magnetic here. No, this is ultra. I'm going to see MHD, which is more impressive than this one. Okay, so just pick up the cold gas and you'll see the resolution. So let's follow my.
So how do you select supernovas or just random?
I'll explain. It's random and plus a supernovae. I'll show you in a minute. Okay, so this is my plot. And could anyone, where can we switch off the lights? The light, yes. This is weird because I should have this on a single screen. Okay, anyway, let's go further. Right, I'll speak about the strategy, what we're doing, numerical issues, and then I'll go into the testing of these models and say why you have to do several specific tests. Then I'll speak about some results, but then you have to hear Nick's talk, where he's going to present all the most important results on this simulation. Okay, so the idea is the following. you know there is a discal circulation. And so, what I think is that I have to look into things not from a local view, but from the global view, and then get the local view. I mean, you don't have to start on the parts and get the big picture. You have to start on the big picture simultaneously get the parts. And you have to set up all the physics with the numerics. But the strategy we take is step-by-step physics approach, which is we add physics by every time, and we learn about that physics. We learn about the feedback of that physics into the interstellar medium. We change the physics, and then we know what's going on. And then we add a new piece of physics, and then again we do the same thing. And we then do convergence studies, which is what I'm saying here below. You must add convergence on your simulations. What means convergence is basically if you double resolution, you end up in a certain resolution where you don't need any more to double the resolution, to increase the resolution, because your solution will be exactly the same. Okay, so we take into account that ISM is a dynamic nonlinear system. There's a continuous disk cycle. The ISM is driven by supernovae type 2 that inject kinetic energy and generate turbulence on all scales. And you'll see this in a movie. We also know that from simulations and from a theoretical paper by Vasquez and Samedine, that run pressure is the main dominant component on the pressures in the ISM. And this is magnetic pressure should dominate below 200 K, and thermal pressure dominates near and in supernovae. Okay, I'm sorry, this is shifting things to the right. So the basic thing we do is, you have here minus 10 kiloparsec to 10 kiloparsec on C. So this is the mid plane. Yes, could you please? That would be great. Right. So now, anyway, this is a cut on a 3D simulation. You'll see the movie later today. This is 1 kiloparsec. This is minus 10, minus 9. This is 0.5, minus 1 kiloparsec. This is the galactic plane. Then again, 0.5, 1, 2, 4. What you see on the vertical scale is basically I ratioed everything in order to keep everything into a small page. Anyway, what you can see here, this is a plot from the time 170 million years after the initial of simulations. And this all is produced, you can see all these loops all over the place. And they go up to 1 kiloparsec and 4 kiloparsec. You see this in the movie later. Okay, so basically you have a circulation, material gets out of here, and goes up here, cools down and falls down. And actually this is a cloud. And you see it like in the movie, this cloud is moving, starts moving from here up here.
Is it wrapped into a magnetic field?
Yes, this is, sorry, I forgot to tell you, this is the magnetic field.
Oh, this is the magnetic field.
Yes. You see the density and magnetic fields like that in the solar. Anyway, so my point is that, as you can see from these loops, all material has to go up, right? And obviously it has to come down, because it cools down and then it falls, and it turns down like this. So basically our strategy is this one, is that I need to divide this into boxes and want to understand what's happening here in this region. Therefore, I need to understand what's happening over there. I cannot miss this gas over here. If I miss it, I miss a lot of info with regard to this one. So imagine you just cut the box here. So you have outflows, but if you don't compensate for the outflow, for your loss, you just run within a small time, you run within out of mass in the disk. So your temperatures basically may drop down. So our strategy is just, you pile up these boxes. Now, I have to warn you that you decide this kind of strategy because you have a goal in mind. Because if you have another goal, then you have another strategy. If you do it locally and say, well, I only want to study what's happening within the first 100 million years of evolution, then you just don't care what's going to happen here or there, right? But anyway, if you interact this box to this one, your boundary conditions here must be the correct ones. In this particular case, these boundary conditions are set up by the program, by the simulation itself. But if you do a cut here, and you say, no, I'm going just to study this box, then you have to define your boundary conditions. Or outflow boundary conditions, reflecting boundary conditions, or periodic boundary conditions. And with the implications, each one of them has. Right? In our case, in our simulations, this is outflow boundary conditions here, outflow boundary conditions there, this is periodic boundary conditions. Obviously, you can say it's wrong having periodic boundary conditions because we are in the radial distribution in the galaxy, therefore things can change. Anyway, this is an approximation. Okay, what we do also, we just divide this into blocks, and then each block is divided into sub-blocks. We do adaptive mesh refinement, but in a kind of a block refinement. So we divide this into pieces, and then each one of these pieces is allocated to a different CPU, and then that piece, that box will be refined again, and then will be distributed to different CPUs. So we basically have a parallel system running. And what is easy here is that I don't need to bother too much with linked lists, which was the old way of programming this, which was a pain and was limited by the memory. You only have to worry about how the CPUs connect to each other and contact to each other, speak to each other. So if you have a parent, which is one of these blocks, and then you divide it to produce two children, then if you divide this one, you produce another two children. So this one can ask to the system itself, who's on my top, who's on my left side, and so on. So if you have CPUs right here, 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 so this one knows who's in this place, here, here, on the top and bottom. So it's pretty easy to set up this in terms of the parallel system using MPI. So just making protocol, broadcasts and communications to the CPUs. So what we do, our strategy is basically we allocate a topology, which is a Cartesian topology, into the CPUs. So everything becomes dependent and becomes more easy to program. This simulation that you will see later is a simulation that started with a uniform component of magnetic field in the plane with a 3 microgauss. The random component was 0 microgauss, and after 15 million years you get a random component of 3.25 microgauss. And the uniform component is roughly 3.1. And the total field is 4.4 microgauss in the plane. Okay, so this is what I was trying to explain, the CPU distribution, and then you just allocate the different CPUs. Right. Now, in order to do all this, we really need to take care of things. First of all, resolution. We have to get correctly the physical process, say the cooling, and therefore you need proper resolution for that. Also, we want convergence of our simulations, and our results must be independent of numerical diffusion, except in the case you really want numerical diffusion to replace molecular diffusion. Now, I already spoke about boundary conditions, and then you have initial conditions. All the simulations has a memory of initial evolution, of initial condition. And you cannot trust a simulation that has a recollection of the initial stage. So this is the case of the signature of the initial evolution. This is a simulation for the galactic supernova rate. I'm including here on galactic supernova rate OB stars, supernovae type 2 and 1b and type 1b in the disk and 1a up to disk. But anyway, this is for 1 time the galactic supernova rate, so this is roughly 2 supernovae per century, and this is 4 times the galactic supernova rate. On red, you see these are average PDFs, that is, we took 50 million years PDFs, 1 every million years, and we averaged them. And so you can see this is for the first 50 million years, and this one is for the last 50 million years of simulation. By the way, our simulations run 400 million years. And you can see there's a huge change between the two PDFs. Basically, you still have a bimodal structure on this PDF, but what this PDF is telling you is the initial setup. It's initial vision, because we set up things according to observations. We take various paper. We heard this yesterday. So you know the temperatures, so you fix everything. You start over with a kind of equilibrium, which breaks up. But the system has to evolve to destroy this equilibrium and to reestablish the equilibrium without having a recollection of the initial evolution. And this is the point. You have a recollection of the initial evolution. And still, still with the supernova rate 4 times greater, you still have it on 50 million years.
Are the areas under the two curves the same?
Sorry?
Are the areas under the two curves the same? Look to be different, right? The later curves seem to have larger area beneath it.
I didn't understand your question.
The area under the curves, they should be normalized to 1, right? The area
Yes, this is 1. This area is 1. This area is 1 for this simulation. They are normalized. No.
It's logarithmic.
It's logarithmic scale. It's a logarithmic scale. This is 10 to minus 2, 10 to minus 1, 1. All this is normalized. Now you can see this. My point is that even for a supernova rate 4 times, you don't get rid of the initial evolution soon. We have simulations up to 16 times and 32 times the relative supernova rate, and here more faster it becomes, you get lost, you lose your recollection of the initial evolution. But still you have that recollection.
As long as you keep 0 in the set, you will always see the...
Oh, never mind. You still, if you do this starting on 30 million years and 50 million years, you get it.
Okay.
Even if you do between 20 and 70, you still get it.
But it would be more convincing to do that.
Oh, well, I can explain that.
I have a small question concerning actually your previous slide. You said you want to resolve the scales, particularly, for example, the cooling. Now, I don't know, for a temperature of 100K and a density of 10 to the 4 parts per centimeter cube, the resolution requirement is 10 to the minus 5 parsec. This is
Yeah, you're speaking of field criteria.
field criterion. So
Yes, that's true. But what we're trying to do is that you have to collect as much cooling as possible. Well, you can't go from 10 parsec to 10 to minus 5. Okay. So, and that also implies that you need self-gravity. And what simulations tell us is that basically when you go up to 0.4 parsec resolution, you get exactly the same distribution as you get as 0.625. And that is telling you that you need more physics, right? And then you can speak about field gravity. Anyway, this is a resolution now. This is the density in the plane. This is a resolution of 2.5 parsec. This is a resolution of 1.25 parsec. You can see the difference between the cold gas and the cold gas here. You can see the difference between here the radar colored fingers in comparison to this one. You see there's a huge difference between 2.5 and 1.25. And even for the hot gas, for the hot regions, this seems to be smoothed out. And you're actually able to trace things here inside of the bubble. Right, this is just to show you the importance of resolution. We have the three resolutions here, 2.5, 1.25, and 0.625. And for the cold gas, you can see for the 2.5 parsec, you get only something, this cold gas is gas with temperatures below 1000 K. You get things you get a volumetric factor roughly of 9%. But if you increase resolution, then you get roughly something around 17%. Even between 1.25 and 0.625. And this means that you're reaching convergence for these simulations. Now, convergence on this particular case cannot be a time scale convergence. I mean, you cannot just take a snapshot and say, this is 300 million years, this is 300 million years, so I should see the same thing. No, that's not true. Because as you're collecting cold gas before, and you're mixing things faster in the hot bubbles, then things will change. What you want to see is on the global properties, if there is a convergence. Now this is a minimum temperature average, and this is maximum density and variation with resolution. And you actually can see that you really need a 1.1 parsec resolution to have the convergence of your solution. Okay, and that is taken from these values here. So what we do, we basically do this thing for these kind of simulations. I've been speaking about simulations and haven't explained yet what we do. Because here this scale, as I said, we take 4 milliliters of evolution. We consider radiative cooling on collision ionization equilibrium. We introduce background heating varying with Z distribution. We have a gravitational field, Fishkin and Gilmore's formula. We have the distribution of interstellar gases seen in observations. We produce Hoffman layer, Reynolds layer, and so on. And we start with a magnetic field that varies with Z. So we assume a kind of partition in the beginning. Now, what is the driving? So the driving of supernovae type 1a with exponential distribution, having a scale height of roughly 300 parsec. Obvious associations. How do we form type 2 supernovae? Well, first of all, what we do is you track for the cold gas into the disk. Then you track for the convergence of that cold gas, the divergence, negative divergence of that cold gas. And then you track for the density and the temperature thresholds. If you have these, then you know that you produce stars there. And what you do, basically, you apply an IMAP, you know the number and masses of stars, and then immediately you get the main sequence done, and then you just wait until the stars start exploding. We also track for the motion of all the stars in the association, as well as for the motion of the association. So basically for the stars, you just give a random speed and let them go straight. Obviously, the larger mass stars, they explode within a few million years. The low mass stars take a long time to explode. So basically what happens is we have roughly 40% of the stars exploding in the field, and scale height is basically 90%, 90% with the exponential distribution. Of the isolated stars, the field distributed stars. Because for the cluster stars it's roughly 46-50%. Okay, now this is a movie. You'll see in a bit obvious associations going off, and the importance in the dynamics of the system. But this is a movie, a plan of the MHE simulation with a uniform initial condition of 3 microbars and random component 0, but then, as I said in the beginning, random component increases to 3.25 microbars. So the total field on this simulation is 4.4. So I'm showing you this because of these 2 clouds in particular. And you're going to see a movie of this, and this thing breaking up to turbulence, and you're going to see an enlarged movie of the cloud, which is this one. This is 1.25 parsec resolution. Sorry. Yes. Well, let's see if I can draw I lost control of this machine. Can you imagine? Okay, this is it. So as you can see, the movie, I will start the movie, and this is 8 million years evolution time. I'm going to restart it. So you have the cloud, and then you're going to see what's going to happen to the cloud. Okay, just breaks up, and you still have supernovae, then you have supernovae going off in the cold gas. But you see shear motions inside and break up this cloud into pieces, and you have a filamentic structure. You have shock compressed layers, you can see it here, and you can see it here, and this one in particular is not destroyed. It's being done and shuffled back and forth by shocks, it's sweep up. but it doesn't have enough density to produce stars. But when we have large clouds, they basically are ruined completely within a few millimeters. So basically, you can consider this metal cloud, and the time scale for this metal cloud is 6 millimeters or so.
So it's an illusion that there's a preferential direction of motion for cold gas along the y direction rather than x. Is it an illusion? Is it isotropic?
No, it's like this. In this particular cloud, you see this happening.
Oh, no, generally the whole box.
No, you see also motions on things moving like this one.
So it is isotropic, it is isotropic in the horizontal plane.
Yes, you start over with that. Okay, so let me show you now. So now I can show you a cluster explosions, what they do into the disk. So here you have a region which we call the local bubble. Here you have the loop one. And how do we produce the local bubble? What we do? We basically know that loop one, we know the number of stars in loop one that come off. So we only have to pick up enough density in the disk where we can produce these stars. So we've done this to get it a consistent way. And then local bubble is produced by 20 supernovae from the Pleiades B1 supergroup, which was crossing by, and then is going to merge towards Scoop-Sen. So basically we track all these stars as they start exploding until the cluster gets out of our region. So here is a temperature map. And so you see the stars explode on a local bubble and then on loop one. And you see there's not much big, you don't see a huge bubbling. And all this has to do with one thing, has to do with the counter pressure effects, with the dynamics of the system. You put up a system you already perturbed, therefore you're running against pressure, and therefore you don't expand too much. And we're speaking about stars with 20 solar masses, and the last star exploding here is 11 solar masses. And here we're speaking about stars with higher solar masses. Now, why am I showing you the local bubble? Because all these models are very nice, but we have to test them. We cannot just say, oh, I have this, and this says this. We have actually to test it. And how do we test it? Well, we normally do tests, numerical tests, to see if your code works, and so on. But you really need to see if what you're modeling can be comparable to anything you know. And basically this, we are sit inside of the local bubble, therefore we should compare it with local bubble observations, say fuse observations, Copernicus observations. So you should take lines of sight through your local bubble, and you should take lines of sight, you place yourself there, and then you take lines of sight, and then you measure, for instance, oxygen 6. And you just go and compare the column densities with the column densities obtained with Copernicus. There's a lot of papers on this, Chapman and Fox 1994. And you do this. Then you can go for emission and try to compare with the low emission measurements as obtained by Shelton last year, and so on. So you basically can test these things. Also, what you can test is, right, we have new results on fuse that tell us the column density ratios, carbon 4 to oxygen 6, nitrogen 5 to oxygen 6, and so on. So you only need to do the same thing. Pick up all these ratios, you just place yourself inside of the bubble, just do a 360 degrees sweeping. You take all lines of sight with different direction, different lengths, and you just take the ratio, and then you just have to compare these. Okay, so this is what we've done for 13.5 million years. Sit on the local bubble. We take column densities for the oxygen 5, oxygen 6. And so this is a 180 degrees plot. So we sit here and then we just make our sweep things like this towards loop one, right? So, and then we get column densities. And you can see the column density for this region here. It's a line of sight with the length of 100 parsec, and you get column density lower on average than 2 times 10 to 13. Now, you pick up all these column densities you can see, And then basically this one comes up to a few for the line of sight with the lens of 400 parsecs, so you cross your local bubble or loop line. And you actually see that the column density is way below 10 to 14. Now, if you just pick up all these and make histograms, you see that the histograms for the column densities basically sit here around 12 something and 16. Now, if you compare this with Shelton and Cox 1994 plots with regard to Copernicus data, you see a similar trend. So we're basically picking up the correct oxygen states. Of course, this doesn't rule out non-equalization. Right. Okay, we can make other tests. We have hydrogen, atomic hydrogen observations, and Eilers claims that for the 1 Newton medium, you have roughly 47% of the mass in the 1 Newton medium, and in the unstable phase. And so what you have is the mass distribution in the disk for the 3 microgauss simulation, which we start with. And what you can see is that this curve here, so this is split on temperatures, and this gray curve, which is this one coming over here, shows you the thermal unstable mass. And as you will see later, the thermal unstable mass is roughly 40% of the total mass of interstellar medium. Now, if you take the 1 neutral medium mass and you make the plot, the history of that plot, you see that the amount of mass we find in our simulation is roughly 55%. So we're basically fitting within the errors the Eilers papers on the hydrogen. Intermediate. And this is consistent with other simulations which are more local, kind of Kritzeman, Norman, Vasquez, and Gasol, and so on, where they claim they have a huge amount of unstable mass, but they don't give you the history as we give. So we're showing you that this is a trend of the system. We're not saying this is only a localized feature. So your simulations have to be able to pick up all these things. Finally, and by the way, I don't want to leave this talk, finish this talk without speaking about volume filling factors. This is a hydro simulation for the galactic supernova rate. This is MHD simulation for the galactic supernova rate. Red is the volume filling factor of the hot gas. And you get the volume filling factor of the hot gas roughly around 17%, 18% for the hydro, and around 20% for the MHD simulations. So this is quite important. Because you know, Cox has claimed, and a lot of people claim that you really need magnetic fields to keep up a small volume filling factor of the hot gas. What you see is that with magnetic fields you still have a similar volume filling factor. But still this teaches also something else, is that the step-by-step approach you're using is the correct one. Imagine we just jump into the MHD simulations. Then we say, well, we have 20%, and well, this is actually what people want. So you wouldn't learn that without magnetic fields, you would have also 20% functioning factor. This is quite important because you're learning the physics. And if you don't learn the physics in this kind of approach, everything fits nicely with your observations, but well, you didn't learn. So this is the approach also Vasquez and 17 in this group is doing. Finally, we can also make a validation inspection. That is, you pick up channel maps and you compare on observation, you compare with your channel maps on simulations. What you have to do, you pick up your cube, data cube, and you transform it in an observational data cube. So you basically transform a 3D cube into a PPV cube. And then you just extract the channel maps. And this one is channel maps for beams of 5 kilometers a second. So this runs from minus 7.5 to minus 2.5 kilometers a second. This is from minus 2.5 to 2.5, and the other one is from 2.5 to 7.5 kilometers a second. And you can see these bubbles here, hot gas, you can see the cold gas all over here. And if you compare this with the LMC maps of Kim et al., 1998, you'll see a huge resemblance. Okay, so to finish up my talk, so the ISM is a dynamic nonlinear system. So we have to take this into account. And we have to be very careful about the approaches we do. We also have to take into account there's a D-scale circulation. This is really important, as you will see in the talk. This is key. We also have to take into account ISM is driven by supernovae basically. We have to take into account numerical resolution. And finally, we have to do fundamental tests to benchmark your models and say the models are okay. At least they give you a reduction of the interstellar medium for this physics you use. Thank you.
Thanks again for a very interesting talk. I'll take the first question myself. I would very much like to see PDF of the magnetic field strength in the final state. How much spread is there in the field?
Well, this is showing this. I didn't show this, but I can give you the spot here. So you have B, you have rho, and your field strength goes in roughly 2 orders of magnitude here up to 1 order of magnitude here for the cold gas. So you don't find B rho 0.5 relation. It's really scattered, and what this means is that you have a lot of ground pressure dominating the disk, and so magnetic pressure is not a restoring force.
So what's the most likely magnetic field? The median value? Is it below the mean?
What do you mean below the mean?
The median value is the one that's most likely, the most common value. And that might well be below the mean if the field is very intermittent. The peak of the PDF, where do you think it peaks?
I'm not sure.
I can't recall the number either, but I mean the number is not very useful in the sense that it's
no, but the information to what extent the field is intermittent is interesting.
What do you mean by intermittent?
Well, that's one thing. One quality of an intermittent field is that the median is quite different from the mean, for example.
The field is always there. I mean, it fluctuates and it has a huge range of fluctuations.
Well, that will cause
Now the symmetrical aspect.
Yes.
Is the symmetric PDF like Gaussian, or it has a huge peak and then long tail?
Well, the upshot of these simulations really is that, as Miguel said, normally people say you can have a Chandrasekhar Fermi law where B scales as 0 to the 1/2, and given a density you can calculate a field and so forth. This actually doesn't hold because it's for each temperature range, as you will see, the distribution is different. So really, if you have a multi-phase interstellar medium, it doesn't make sense.
But it's also
obtained in such a way.
It's also a misunderstanding to expect it, because observationally it's there only as an upper envelope. It is there as an upper envelope observationally. It's not you better predict.
But it's also known that if you make a scatter plot B against rho V squared and sigma V locally, then the correlation is much tighter. So B squared rather scales with rho V squared rather than with rho. In this sense, it's better to check.
Well, as you will see in my talk, I think the real physical reason behind it is that because we have lots of, as Miguel said, when pressure-dominated flow, we have lots of even super-alphenic flows which are created by fast magnetosonic waves. And what the Chandrasekhar Fermi law basically says is that the turbulent velocity scales with the alpine speed, and this definitely does not happen here. And therefore, you get this huge scatter. I mean, that's really one of the results. Here is the figure we are talking about. So if you really look at it at the various colors, which is different temperatures,
So this is cold gas.
and if you look at E versus rho, you
And
see
the gray one
it
is
is a large volume.
the thermal unstable gas. The thermal unstable gas will see a large volume. So this is divided by the phases by the so-called phases due to
Yes. Obviously, this thing is resolution limited because it will never stop. If you increase the resolution, the observational plot goes to milligauss or and even above at higher densities. So we should understand that the upper right corner of this plot is certainly resolution limited.
But yeah, I mean, we have, of course, a limit in our densities due to resolution. As Miguel said, we get something like 100 or 1,000 to 100.
And a really useful correlation between the upper envelope of B with density.
Well, that may well be as we get to the high densities and low temperatures, then this scaling gets much better, of course, and because then the flows become magnetic and dominated.
One also needs to realize that this is the way observers see it. They measure, they look for a field, and they find a field.
Yeah, but it depends, as you see, where you look, at which phase of the interstellar medium, so to speak. Yes.
Okay, here's the plot showing you this is a histogram in reality, but this is the average pressure, temperature, thermal run pressure, and magnetic pressure. And this is a plot that shows you for the range of temperatures. So what we do is we beam the temperature, and for that beam we calculate the average pressure, right? Mm-hmm. And so you see that this is black is the thermal pressure, red is the magnetic field, and green is the run pressure, and red is the field pressure. So you can see that run pressure dominates most of the flow between 200 K.
Except at low temperatures.
Except at low temperatures, temperatures where thermal pressure dominates. And you can see also here that for the magnetic pressure, that's basically saying that magnetic and thermal pressures are independent.
More questions?
They had runs with different imposed magnetic fields. You mentioned 3 microgauss, right? How the filling factors, for example, depend on the field strength. Can be assessed as a function of field strength, right?
Oh yes, I have plots of with the field strengths, and let me see. We've done calculations for different field strengths between 0.25 microgauss up to 3 microgauss, and therefore your volume filling factor is basically similar. It's the same almost. It doesn't change much between the 0.25 passes.
That's fine, because it's
the
unimportant. When
yes. And it makes sense because in the yes, and then you end up on the limit because our limit is 3 microgauss, therefore then you don't see much variation in this case. I don't know what's going to happen if you increase the magnetic field. But that is something we have to do, but we are limited on time, computing time, because
So, if I can add to this, I think if you increase the magnetic field, of course, the volume filling factors
Will.
can change, but not by much, but not by much.
They will increase, they will decrease most probably, right? It's horizontal.
And the main reason being that, of course, in a 3D situation, you can always push field lines aside, and once you create holes, you can have the flow go up there. I mean, the problem was with 2D simulations previously, you always had to work against magnetic tension really hard, and this is why people told us that breakout of super bubbles is very rare, unless you have high energies in the bubbles. But in 3Ds, I think this is not true.
But so this one looks to be strange to me. You have larger filling factor on the hot gas with a stronger magnetic field. I would expect, this way or another, even in 3D, I would expect an opposite tendency.
Not necessarily, because of course you really inhibit outflow to some extent. You have to do this, but you don't prevent it. That's the point.
Yes, but still, they can facilitate the formation of the hot gas. So that the marginal increase in the filling factor with magnetic field looks strange. Perhaps it's just coincidence.
Also, the compression, of course, in shocks is lower if you have magnetic fields to compress. So I think on average, if
you contain the gas and you prevent it from escaping, then is it a big surprise that you have a bigger filling factor? Maybe not.
A smaller. If you contain it stronger.
No,
okay.
You prevent it from escaping, cooling.
So the tendency is you really reduce the escape, but you don't prevent it. You have always escape of gas, but not as much as without filling.
Do you mind I show this? Just to give the impression of the data?
So it was the filling factors in the whole box up to height, large height, or within some height. Then what filling factors will show?
In the disk.
I showed you on the disk.
Right.
And so we have to take into account if you increase the magnetic field in the disk. So we start over with. Now we have to take into account also the circulation, and as soon as you just break out, you release all the hot gas. So I would guess even if you increase the field, then you contain the hot gas there, you're pushing it out, but it takes a longer time to break out, but it breaks out. And as soon as you get that out, you just have an open valve to put things into the air. And that's what we see on this simulation. So, and this you see it on the HD simulation, moving towards these 3 microgauss, starting from 0.25. So it might also happen on larger field strengths. It will take longer time because what you see on the simulation is that it takes longer time to break up. But as soon as it breaks out, it's usually it's open valve, basically. Can you, I mean, the boundary conditions on the top and bottom, do they not leak magnetic fields out so that the field would need to be and could be replenished?
Well, what we're going to show today with it is that you don't see much outflow of the field in the boundaries, in the outer and bottom boundaries.
So does this mean that the field is not strictly imposed, but in principle it is almost fixed during the course of the entire simulation?
What you mean?
Frozen in, you're actually losing flux, but it's a very small amount.
But it's not a small amount. On the total amount of mass you're losing on this simulation is 10%.
Right.
So the flux you're losing also will be small.
But you could in principle replenish flux because you have turbulence and dynamo action.
Oh yes,
Oh, yes,
don't
yes.
have dynamo in the simulations, but
Why
we
not?
had.
Are you sure? What is it?
Well, I mean, we don't.
We don't do differential rotation.
Yeah.
No, small.
Oh yes, you can do small scale dynamo, yes, with the double dimensions. Probably that's what we do, because we have this increase on the random component.
Yeah.
But what is interesting is that random component increases. We have this on this paper we submitting, and it increases very fast, and then it stays oscillating over there. I can show you the plot.
It increases very fast because you get from the smooth state to an intermediate.
Yes, exactly.
And that increases the mean energy. But then the question is if you see a slow rise.
I don't see I see this jump. I can show you the plot. So you see this jump, and then it becomes like this all the time. So you basically reach the
one very important factor here is that the magnetic field resides mostly in the dense gas, and the dense gas is moving much more slowly than the hot gas. So the dynamo action is not that very powerful. One really needs to not just measure the mean RMS velocity, but think about where it is.
Well, I would think that alpha omega dynamo would be probably much more efficient than omega.
What was the last one?
I
you said something about alpha omega.
If there's shear, of course, yes, then it's more efficient, you're saying, of course, yes. Is there actually even Coriolis force?
No, there's
no Coriolis force,
alpha omega dynamo.
So we're trying to set up that, but first we're going to the lateral phase, self-gravity, and so on, thermoconduction, certain thermoconduction issues. So, and non-carbonization is the fundamental step we're doing at this moment.
What about the turbulence intensity? Is it increasing with the vertical coordinate or decreasing? The average, the turbulence intensity.
RMS velocity. RMS velocity is high.
Yes.
Oh, I haven't done that part yet on the vertical structure.
Yeah.
We just got this data. I dealt with this data a few weeks ago.
What do I expect?
I would expect it to decrease.
Decrease. You said.
It becomes hotter time.
Oh yes. If it becomes hot, it becomes faster. That's true.
Now we expect the opposite.
No, I also expect the opposite. It would increase.
Increase.
With height.
Yeah.
Okay, we're running a little bit late, but not more than we lost in the beginning. So let's go on to Sandy, which is talking about the correlation between supernova rate and velocity distortion.
You might go on for some more discussion and have to restart because
Still in the fact loop information about how to get there as well.
Yes.
But this way.
I hope you all will find the information about how to get to the place, the dinner place. One way to get there is by walking. That takes a little bit more than half an hour, so we do have 45 minutes. We can just make it reasonably okay. But there's also buses, and does anybody local know what is a good bus? Is it 43 still okay? But that only goes to North Hall, not very nice. What? You don't even know where it is, right?
No, we don't know what restaurant we're going to yet.
It's Spiegelhuse, and I'm just filling in the time here for him. But I mean, it's roughly southwest from here. And
During summer season.
So the leader will supply it with compasses for us.
Sometimes we have some transparencies for old things from one of the previous meetings, but I don't think so.
Actually, I have here the bus routes on this step.
yes.
Like you did your schools.
Okay.
Okay, so I'll be trying to present you in this talk a particular aspect of supernova-driven turbulence, which is how does the supernova ray correlate to the velocity dispersion. This was the title of my talk. I don't know if you see supernova there. My collaborators are Eric Bell at the MPIA and my supervisor Andreas Doctor, which is now reunion.
Need more power? That's 300 volt.
But something must be wrong with the projector. Huh? There's almost no, it's just supposed to be intensity. Is that true?
We shall find out with the next speaker.
Oh, look at that.
So as you know, the interstellar medium is quite turbulent, as Miguel has shown. The turbulence has different aspects. It's known to be supersonic in dense molecular cloud, subsonic in pre-stellar cores, and transonic in the diffuse medium. Now, turbulence is important in the interstellar medium because it regulates star formation. Regulates star formation in the sense that you can have cluster star formation versus some isolated star formation. You can have fast star formation or slow star formation. So it's important how turbulence is generated, what is the length scale on which it's injected into the interstellar medium, what is its strength. So one has to look out in the interstellar medium and try to understand what is the role of different turbulence drivers. As you can see, there is no shortage in the turbulence drivers. The interesting thing is to isolate them and try to understand for each of them what is the scale in which they inject energy into the interstellar medium and in which amount and what they do. And study the cumulative effect. So, for example, there is, of course, supernova explosions. There is a number of others which have worked on that. Stellar winds and outflows from young stars. Alexander Boson and Michael Smith have done a lot of work on that. Thermal and gravitational instabilities might play a role. Fabian Hatch has studied the role of propagation of alpine waves in the interstellar medium and the energy they deposit there. Also, magnetorotational instability might be of some significance in the interstellar medium. I think there is a number of people in the audience which will speak in more detail about it. And you might think also of other perturbation, large-scale perturbation, which could stir up the gas in the galaxy, like repetitive minor mergers, tidal interaction, and the effect of ground pressure. For example, for the particular galaxy, which is Hornberg 2, which is a dwarf irregular galaxy, with Andy Buckler, we showed that by comparing the H1 morphology in this galaxy to static H1 maps we produced, we showed that the kinetic energy is injected into the interstellar medium of Hornberg 2 on a scale of roughly 6 kiloparsec, and which could be understood by a combination maybe of tidal interaction and ground pressure in the group where the galaxy sits in. However, for our galaxy, for the Milky Way, McClough and Pleasant did some analytical estimates of the global energy input into the interstellar medium by those different physical processes. They come out with numbers that show that the energy input from supernova is a factor of 100 higher than the sum of the other processes. So one would think naively that, of course, the turbulence is, you can forget about all the other processes, and what is important is only supernova. But of course, this value is global, so one has to look how does this vary with radii in the galaxy and eventually with height. Now, as I said, the dependence on radii might be a clue on the competition or on the role of the different processes. So, for example, you have this galaxy NGC 1058, which was published by Dickey in 1990, and we see that the velocity dispersion starting from a given radius starts to flatten.
Sorry. More or less standard problem with such combinations. How much of unresolved regular gradients contribute to the observed sigma at small radii? What's the resolution of observations? If it's comparable to 1 kiloparsec, then differential rotation will be the seed here to be velocity dispersion.
In the central parts, presumably the velocity dispersion measurements are pretty bad because of smearing effect. And I will try to show that. But there should be no problem in the outer parts. So the steepness of the curve might be wrong, but the fact that it's flat is
that the turbulence?
Yeah, so this is the...
Now it decreases with height.
Radius.
Sorry. Radius, yeah.
So this was old observations in 1990. We went to the literature and compiled a number of measurements of the velocity dispersion. Here it's shown as a function of the supernova rate. So each point here is a galaxy, actually, so it's not readily resolved values. And you see that, again, there is something for values less than 1 times the galactic supernova rate, the velocity dispersion goes roughly flat. In particular, here, for example, the highest point, those are starburst galaxies. This point here is NGC 2915. So this is the central part of this galaxy, and this point here is the outer part. This point could be in reality here because it has a star formation rate of 0 in the outer parts. But this still has a velocity dispersion of around 7-8 kilometers a second. So yesterday Eric sent me actually even more observations than this time. So the previous measurements were a global measurement of the velocity dispersion in the galaxy. So the velocity dispersion is using the neutral hydrogen 21 centimeter line, and the star formation rate is derived from UV or B-band observations. Now we have two galaxies where we have the star formation rate radially resolved, and this is with H alpha you can have at the same time the star formation rate and an estimate of the velocity dispersion, though it's much more noisy. And you see again that there is this flattening. The shapes are quite different, so there might be some. Both are spiral galaxies, but this one has a steeper density profile. So the flat regime in this galaxy might be only this one, whereas it's extending much more than the other galaxy. So this problem motivated us to make some simulations to try to understand how does the velocity dispersion correlate to the star formation. Because normally, if you take any star formation law, whether the Schmidt law or Kennicott law or Silk law, and they have different dependencies, but all of them tell you that star formation is decreasing sharply to the upper parts of the galaxy. So naively one would think, okay, if there is no galaxy, the gas shouldn't move. Basically, it should have a very small velocity dispersion, which it hasn't. So we tried to test that. Was first with we started with very simple simulation. So we used the Zeus code with in 3D with a 128 cube resolution. We start from a zero velocity, uniform density of 0.5, initial temperature 10.4. Since we were interested only in a cycle of the simulation where kinetic energy reaches equilibrium, and it was relatively quite fast, we didn't account for this vertical height in the specification, so it involved periodic boundary conditions. And okay, there is no specification, magnetic field, and gravity to this point. The relevant quantities are then the cooling rate, the cooling function, the average density, the supernova rate, and the efficiency of the supernova feedback.
And also how you turn on the supernova. Where do you turn it on?
Yes, there is an effect. I will present it. For the cooling function, I used, for the time being, I used the solar metallicity cooling function, which is composed of two sets of data, Galgano and Craig, all data in 72 in the low temperature regime, and Galgano and Lupita in the high temperature regime. So the supernovas are, since we are blowing them based on a rate, they are then equally spaced in time. So the deep delta T between two explosions is 1 over the rate, basically. We assumed our estimate of the galactic supernova rate to be this value, which you can obtain if you assume a frequency of 1 over 57 years, and a scale height of supernova type 2 of 90 parsec, and galactic radius of 15.5 kiloparsec. Of course, this is not so crucial because we are going to do simulations with different rates. So if you use your another definition of another value, you can just shift the curves. The site of explosions of an explosion is chosen randomly, only under the condition that the average density is higher, that the local density is higher than the average density. So this favors a bit clustered supernova formation. You can we faced in the high rate simulations that sometimes the interval between two supernovas might be smaller than the CFL time step, and because this is fixed by the type of supernovas, then at each, in this case, I need to detonate different supernovas which are equal to the number of to the closest integer of the ratio.
So TCFL is what?
The Cohen's division.
That's the time step.
Yes. But so you might have, you might have, because of the very high rate, you might have a time interval between two supernovas that might be smaller, and you cannot have to put them at the same time.
So, what is generally the time step?
It's about 10 to the minus 6 in gold units, which is 1,000. Yeah, 1,000 years or something like that. Okay, so each then there is the other efficiency parameter. So the total energy is assumed to be 10 to the 51. Some of that energy is transferred into the medium in the form of thermal energy for this time. The rest might be lost in cosmic rays or neutrinos. I distribute the energy around the explosion site on 3 cube cell with a Gaussian profile, taking into account the fact that a bit of the geometry, because the different cells around the explosion cells have different distance to the center. So there is face cells, corners and sides, and they get the ratio which is proportional to 1/2 of the energy you have to put, which is left for those cells, so in a ratio of 1, 2, and 3. So the ones on the corner get 3 times more than the ones on the face, just to preserve more isotropy. This is 2 examples, 2 frats in the simulations. One is for 1 galactic supernova ray, the other one is for 0.1 galactic supernova ray. You see that the structures are kind of completely different.
Both size is what?
It's 1 kpc. So you see that the supernovas are blown off in the dense regions. I don't have movies as Miguel, but I think it's much better. Okay. First thing we looked at is to let the simulations evolve until kinetic energy equilibrium is achieved, and then so this is the kinetic energy for different simulations. And then what I did is to take up a time step when this happens, when the equilibrium happens, and do the analysis and the measurement of the velocity dispersion. So first I tried to do it like how observers would do it, is to define a beam size. I use 16 squared beams and plot the distribution of the velocities along line of sight. For example, these are 4 examples in this case where the rate is 1. And then fit the Gaussian there and then measure simply velocity dispersion. And then to obtain a characteristic value or average over the number of rings. So for example, for 1 galactic supernova ray, velocity dispersion obtains 8.63 kilometers a second. And I did this for the total gas and also for the H1 gas, where the H1 gas is defined as being simply below 12,000 K. Just did then, just for being sure, I wasn't sure I was doing the right thing, sure that there is no bias there. Just plotted the PDF of the velocity module in 3D, and then the peak value here is around 11, but the average is about 14.9, and then if you divide this by square root of 3, you get exactly 8.6, so it can make some sense. So now I'm going to present you some different simulations. First, both are simulations done with a particular rate, 0.1, the galactic rate, and with different feedback efficiencies. So the efficiency is gives 100% and 50, 35,
So
10, and
it
5.
means to me that the amount of energy injected in each supernova event, right?
And you see that, so this is the velocity explosion. We obtain this, the upper one is for total gas, and then this is for H1 gas. So you see that above value of 25%, there is a saturation effect which is taking place.
Maybe you should plot energy versus energy, square. Velocity square against energy.
Yes, and only with the logarithmic scale you can produce something like a continued increase. Can it be 1 cube? 1 cube would look very similar. 1/3 cubic root.
Okay, I mean, you mean plotting this in the graph.
So, I mean, he is assuming Kolmogorov scaling, that's the question, whether he has that.
In power law with power less than 1 would look very similar. Can be no saturation, can be power law increase.
Just checked in the literature, there is this paper by Fountain and Steinmetz and collaborators, where they estimated what would be the amount of feedback from supernovas, and for a solar metricity average density of 0.5, they found something that's about 20%. So of course it's difficult to cover the whole 2-parameter grid. You cannot do simulations of varying the whole parameters. So I then choose an efficiency of 25% and did simulations with different rates. And this is the result we got so far. And it shows that, so for the total gas, these are something like starburst galaxies eventually. Then there is a plateau in this region, and then it might go down. But if you look in the H1 gas, it might be completely flat as well. There might be also still a small effect here. However, what I must say is that though in all simulations kinetic equilibrium is achieved, thermal equilibrium, particularly actually for only now for those 2 galaxies, is delayed. It might be simply, it takes more time to achieve thermal equilibrium. I think this is an artifact of the simulation, because what happens is that we choose randomly the site of the explosion just under the condition is higher than the average density. But it might well be that we are choosing, we have more cells which are in the intermediate temperature regime and not sitting at the low temperature regime, and we are blowing supernovas there before they completely cool down to the minimum temperature. So you are putting always more energy than you allow the system to cool. So in another sense, we are not blowing the supernovas always in the densest cell. So you have to iterate a lot of times. You have to have a lot of events until the global cooling rate is equal to the heating rate. So this is why thermal equilibrium is a bit delayed. The reason I'm mentioning this is my explanation of the flatness was in the first place, and it still is, but to confirm that is that there is a combination of supernova driving and thermal instability taking place in particularly in the cooling shells, and this means that for those supernova rays which are sitting at the end of this plateau, they have more cooling, which compensate for the less direct driving, because they have time to cool furthermore. So it is balancing the lack of the less driving, and so you have more cooling in this regime than in this regime, and so the curve remains up. However, there is also another effect here, is that all simulations have the same average density. And in reality, you might believe that there is a correlation between the average density and the supernova rate. It means that, for example, for those particular simulations here, which have very small rate, they might be happening in a very low density medium, which is at lower density than what I use. So currently I'm doing some simulations with lower density here, and a guess is that this curve will go again flat at the lower end. To convince you that there is some thermal instability taking place over the supernova driving, I did a number of simulations where there was no thermal instability, means that the minimum temperature was clear cut at 6,900 Kelvin instead of 100 Kelvin, like in the previous one. And you see that there is a decrease with the rate. For example, at 0.1 you have values.
The state is different now than in the previous talk.
Yeah, here there is. No, there is, yes, because this is an older plus I didn't. The range is. But this is the same simulations, basically. Okay. So what are my conclusions up to now? Because this is basically work in progress. I mean, unfortunately, I don't have. I said, you think? I said, you said 9 months for one simulation.
9.
His simulations. Mine, I cannot afford it because PhD time has no mercy. So, conclusion so far is that the velocity dispersion, particularly of the H1 gas, seems to flatten for values of the supernova rate which are smaller than 1. The plateau is likely to be caused by an interplay between the supernova driving and thermal instability, particularly in the cooling shells. What you might have seen is that probably didn't mention is that if you remember the PDF of the 3-dimensional velocity field, it's not showing a Gaussian. I can maybe jump quickly back. It's not showing a Gaussian profile, rather it's something like an exponential profile. I mean, this might be of importance for people modeling a molecular cloud and starting with a Gaussian field in their cloud.
Is that so different from a Maxwellian?
Yes, it should be Maxwellian.
Yeah.
But it looks okay.
I have to maybe make it fit. Then this point is that this kind of result, if you can obtain some velocity dispersion, wave relation, eventually correlated also to the average density and eventually to the metallicity, this might be of some use for the people doing galaxy formation, particularly for the semi-analytical modeling where they form halos and they have velocity dispersion and they don't really know how much amount of feedback they have to put in. So this might provide might be useful in that context. What I've started doing now is investigating other ingredients, particularly now the effect of having a different density. Then I'll move on to having different cooling curves for different metallicities. Then, of course, you have a whole list of things to do, particularly including magnetic fields, stratification, and then supernova type 1A, which were not included here. The problem here is that there is some correlation between the rates of type 2 and type 1, but the errors on the type 1A supernova rates is very high. But in principle they could be included, and eventually something about more physics like cosmic radiating affecting the whole box. So that was it.
Thanks very much. Questions?
So, if I understand correctly, that this increase in that global velocity dispersion with supernova rate can be related to the fact that as supernova rate increases, you have more hot gas, which has obviously a larger speed of sound, larger velocity dispersion. Have you tried to plot the filling factor of the hot gas together with the velocity dispersion to see if the two curves will look similar?
Yes, so okay, I'm calculating the filling factors now, but I haven't done yet systematic plotting because, as I said, for some range of the rates here, I don't have conversions yet. So the simulations are still running. So kinetic energy is converged. I'm waiting for thermal conversions here, which is happening but just delayed. And then I will be able to plot it for the whole rate. For example, in those, the interesting part is actually here. For those simulations, the filling factor of the hot gas is 1. Basically, you don't have.
What's right here?
And for this simulations, it's also very low. The interesting thing is in this situation. But this is something that.
So for this velocity dispersion, this way or another, it must be related to the speed of sound, right? So that's kind of very strong the speed of sound.
Also, the magnetorotation and stability is related to the speed of sound. This is the maximum possibility. I have no problem to understand that you get some 5 km per second or even 10 km per second by so many supernova explosions. But it's also no problem to find with the magnetorotation and stability 3 km per second. How can it be true that in your introduction you underlined that the energy of the supernova explosions is 100 times larger than all the others?
Simply can't be true.
Yeah.
But that wasn't his paper. He was just referring to somebody else.
This was particularly referring to our galaxy on one hand, and it's a global quantity. It's not defined with radio.
Yeah, that applies for the star-forming regions. It's 100 times more energy in the star-forming regions. If you compare the supernovae and MRI.
Yeah, this is not easy to compare the energies, as the source of the energy in MRI is the rotation. And yeah, this is the rotation. It's not as you yesterday, it is not the input of energy by explosions, it's the rotation. And in so far, it is not easy to compare the energies. The result is, if one simulates or you do, then 3 km per second are possible.
Yeah. But Mordecai's estimates were based on some numerical simulations of MRI calculated. But in the star-forming
I don't believe it, shortly speaking.
It's square distance, right? Anyway, MRI produced about 10% of the total energy input. Well, 10% of 1% still kind of order point quickness.
At the moment we get 3 km per second.
Peter? Yeah, I was wondering if the inclusion of the galactic fountain would make a large difference for your
stratification and
yes, especially if you go to higher star-forming rates.
Necessarily, this would make some difference, but I cannot, of course, since I haven't done the simulations, I cannot really answer confidently.
But we can ask and he asked questions, so maybe you can.
So it might be that the high velocity clouds might appear as a separate population. So it will not affect your velocity dispersion. So you will have two separate quotients basically. So you'll have, but there might be some overlap also.
But also by the fact that you get rid of some of the energy into the halo, which would not be then available for producing shear flows in the disk, for example, that should have an effect also on your velocity dispersion in the disk.
Yeah, I mean, of course, this is one of the points I want to put the effect of stratification, but we wanted to get basically the raw basic relation without more complicated physics.
Just to reduce this growth, right?
Did you drop your question in favor of copy or what?
No, it's a simple question, just.
But I would like to make a suggestion. suggestion to anybody doing this kind of work, including ourselves. It would be very interesting to do the following. We assume that the kinetic energy dissipation rate scales as rho u cubed. Okay? So one simple thing is to just make that assumption and check how much energy goes into cooling, how much energy goes into kinetic dissipation, etc., and make those graphs of those ratios. But a more clever thing would be to actually measure the kinetic dissipation, which you can do, and check if it scales as rho u cubed, because this is complicated and maybe doesn't quite follow from the world in this situation. It can be done. One can very easily make up the actual energy budget.
Well, what you learn from that, okay, why you don't need to know that?
I just would like to know.
If let's
how much goes into cooling, for example?
I think roughly we know these numbers. I think both for your simulation and for my simulations, the number was approximately 10%. 10% of the supernova thermal energy input goes into kinetic. And the same 10% of course goes back into the heat again.
Yeah.
And then the 100% goes back out.
I would be interested to see if it's the same in the gas with so much higher salt.
Yeah.
I think it's a
And
lot.
how it varies with ETA.
You don't know that in your case?
No, somehow you can have the velocity, turbulent or RMS velocity 10 kilometers per second. You immediately can calculate how much energy has been converted into kinetic energy. It will be about 10%. Well, just know that the kinetic energy of turbulence is 10 kilometers per second, right? You estimate energy, you know how much energy you have injected. 10% will be there roughly. And this will be converted into heat. There is no other way for this energy to do anything else. Perhaps some will go to magnetic energy, the rest of the heat. And again, the heat emission.
The ratios might depend on ETA. Probably when you lower the input rate, you don't kick as much up into...
Yeah, that's a different question. How this depends on different galaxies with different supernova rates. Yes.
But I think we need to stop. We're a bit late, but let's go for coffee for 25 minutes until 4:15. And thanks to both speakers very much.